So today I've got this really cool INFRANOR wheel motor for an AGV. This would deliver power, 20 millimeter diameter, 200 millimeter diameter, and 0 to 2 meters a second, running at about 2,000 RPM at the motor. Probably do 4 meters a second, or 4,000 RPM at the motor. So this is a 10-to-1 gear. It's very efficient. It doesn't, it's been running overnight and it's still not even getting the least bit warm. This motor, a low profile 48 volt winding, 10 amps continuous. That's like 8 amps RMS, maybe 3 or 4 times that for peak. For several seconds, I'm sure, and then a low profile feedback device, incremental encoder, commutation tracks, and an index. I'm tracing the index here off of the Copley drive. That's a AEV module. This can do 50 amps continuously. So you could run, I don't know, maybe 30 amps for 10 seconds to go up a hill or a ramp or something. Or to get up to those top speeds to accelerate a mass. This AEV or APV module is plugged into a development board, and I've got this riding on the back of a XP power supply with, it's a dual power supply, 48 volts for power. Maybe it's only a 5 amp supply. Typically the AGV will have a battery system, so maybe you don't have to worry so much about current limits on a power supply, but there's also a 24 volt supply in here for keep alive, or if there's brakes or whatever auxiliary stuff you have, so to keep alive. You could also run the V-logic off of the 48 volts. Just make sure you don't regen up past 65 volts. Maybe in the future I'll run this thing with the Nano, or try to get an integrated thing closer to the motor, but this will do 70 amps peak, 35 amps continuous, where this is a 50 amp continuous. No heat sink right now. It's just warm, delivering several amps, but you can mount that to the plate or the frame of the AGV. And of course, with EtherCAT, Ethernet, you get Ethernet IP, Modbus-TCP, UDP, CANopen, and TJ1939, a simple CAN standard, and could be run off of like industrial PC, 24 volt powered. What's a type of Neosys industrial PC with, could be either CANopen using a capacitor PCI Mini, or just Ethernet, EtherCAT, or even the serial port, 1 axis or 2 axes for power. Could also be 4 axes for control, but typically a steering system would be used. So we'll just take a quick peek at the drive. And so I'm using the AEV-090-50, 25 amps continuous, 50 peak. There's a version that does 50 amps continuous too. And that's mounted into a mounting board. For convenience, you could lay out your own board. And again, I'm troubleshooting the index here. So I'm looking on the back of the easy board to see where to monitor the index. And it's on the feedback connector with the Hall tracks. So this is I'm just clipping on pin 9 with respect to ground on my scope. So just to go through the basic setup here in CME, we'll take a quick peek at that. It's a brushless rotary motor. There's no brake. There's a 10-to-1 gear on it, incremental encoder on the motor. I'm not using the Halls because I'm having this weird index drift, which affects the Halls, but the encoder works just fine, 8192 counts per rev. I'm using an analog to command position over time, or velocity. And the motor data has been entered. INFRANOR BR-2 motor with a 10-to-1 gear, 20 pole motor, 10 electrical cycles per rev, so good pole count. I didn't see any cog in it. The motor's got some inertia, but then you got to add the wheel or the reflected inertia. But this is okay for initial tuning. 0.8 Newton meters, a torque constant. I think they give it in Newton meters per amp RMS and volts per radians per second in RMS. And then the motor has some resistance, low resistance, so very efficient. At 10 amps, it's I squared R, so maybe 7 watts. And then low inductance, 0.4 millihenries. This should be able to go down to 100 microhenries without a problem. And of course, we have a tuned up current loop. I just set some low current limits here for the bench. But again, you could do, the 10 amps continuous, 30 peak, 40 peak, 50, whatever you need to get up the hill. And then the velocity loop was tuned basically just with the wheel. I set the limit out of my way here. And then position loop, I just knocked the default value down 50% in case the inertia mismatch got big. But again, there's no vehicle here, so I don't know what the reflected inertia is going to look like, but I'll start off halfway from the default, assuming the inertia will be big. And then for my analog profile velocity command, I've chosen 6,000 RPM at 10 volts. I'm just using an offset parameter. I don't have an analog voltage. So get from RAM0X1A. So this would be a scaled speed. I can set this to any offset value I want so that I have a command for voltage. And right now I'm doing about 3,050 RPM based on the voltage command. And again, I've been tracking the index pulse. So right now it's working from the 0 position, which is good. And so for the troubleshooting of the index, what I do is I do the homing, and I'm going to have to do this twice, but I go to the index pulse for 0, so I'm all lined up, and then re-enabled and commanding speed. I'm just going to monitor this index pulse. It's really narrow, but I'm triggering off of it. And then you can see the Halls decode in a logical manner. And then what was happening over time is I was drifting away from 0. But let's goose up the speed a little bit. Set RAM0X1A to, that's the value I had, let's double it. There you go, a little faster. So I'm just changing the analog command for velocity. And away we go. And you can see it's already started to drift away from 0. So here's the index trigger, and it's drifting away. So there's maybe there's a rubbing noise, maybe it's a mounting problem. You take a quick peek at the motor spec here. So the INFRANOR motor, and it's got 8 amps RMS, resistance, inductance, back EMF constant, volts seconds per radian or volts per radian per second, 0.06. That's RMS. And then the Newton 83 for stall at 8 amps RMS. And the speed at the output of the gear, 500 RPM. So that's 5,000 at the motor shaft. And we can see INFRANOR has other low-profile torque motors for perhaps larger currents, larger torques, and lower speed. So not every motor's got to go that fast. 48-volt windings, very, very good design. You're not using a winding that's really a 200 volt or 100 volt winding. You're getting the torque out of the motor that you desire. And then this was the encoder here that it's a low profile capacitive encoder, low cost, programmable for different motor pole count. This is a 20 pole motor and 8192 counts per rev, or 4096 default, which also note that there's some limitations on speed based on your counts. So with the 2048 line, it looks like 8,000 RPM, so that's good. So the resolution, if the resolution was goosed up, which I don't think is necessary for an AGV, you'll have to limit the speed here. And again, so I'm just troubleshooting the problem of how come I can't do trapezoidal commutation, because I've got some drift here. But let's take a quick peek at the calculation for the energy. I'm going to assume 480 watts, that's 48 volts at 10 amps. So 480 watts for 10 seconds. That's at 2 meters a second with 500 pounds, I got 453 joules. So that would be 500 pounds at 2 meters a second, 480 watts for a second. Watts are joules per second, so times a second, and that's about right. With this motor, of course, you can get 2 or 3 or even 4 times the rated current for a short period of time for acceleration. But I'm just looking at the kinetic energy of, going from no motion to full motion. How much joules do I need? And of course, we could do 480 watts for 10 seconds. So maybe that's a slightly larger mass. Yeah, so there's other places the energy comes out. The motor warms up, the gear inefficiency, the wheel efficiency. So maybe not that much mass. So there's a lot of other physics that gets involved with the vehicle.